Good afternoon and welcome to this international gathering of GNU inquirers, shall we say. A real mixture of expertise, the second in the series, and a great thanks from the British Astronomical Association Radio Astronomy section to Marcus, who's leading this afternoon. The link will be posted, and the seminar can be viewed on our YouTube channel in due course. I think that's all from me. Marcus, I'm handing over to you. It's all yours. Thank you. Does Marcus have a comms problem? Ah, there we go. Your audio is not great for me.
Okay, I'll adjust the audio here in a second. I thought I had adjusted properly, but apparently not. That's okay.
Yeah, it's not great for me. I don't know if it's at my end or your end. Comment from
No, it's the same for all of us, I think.
Oh, yeah, thanks, Tony.
Okay, how's that?
No, that's not better.
Okay.
It sounds like you've got about 1,000 times too much gain on your microphone.
Okay.
Totally distorted.
Now it's gone quiet.
Must be one of those GNU Radio blocks that's wrong.
Yeah, Marcus, you're off altogether now.
Yeah, keep the feedback going to Marcus. It's always helpful.
Yeah, we can't hear you at all still, Mark.
No, same as before.
Again, no?
That's back to the distorted sound, yeah. No, distorted.
Okay. Let's see if there's some setting that I can set up some. Let me bring up some actual interesting stuff here. Okay, I'm going to share my screen. Can everybody see that?
Yeah, that's working.
Yeah, we got it.
Okay, good. Oh my God. Okay, thanks for your patience, everyone. I did do some testing beforehand of my setup, but clearly it was insufficient. So welcome to part 2 of the GNU Radio and Radio Astronomy series. I don't know how many of you were here for the first one, but I'm going to assume that many of you were, and we're going to dive into part 2. If people need a review of the previous work, let me know, and we can maybe we could do that now. I could go to the other slide set, just dive right in.
I suggest dive right in, and
okay.
the video is on our YouTube channel for the last one.
That's true. That's true. So what we're going to talk about today is interferometry, which is a new thing that I've added to the BA seminar, and something that a lot of people should probably try at some point in their radio astronomy career. And we're also going to talk about the data outputs, because we didn't discuss that the last time, what the actual data looks like. So I've added a few things to the seminar application, and we're going to go into that in a little bit and open it up and see what's new. So there are now 2 inputs instead of 1. What that allows us to do is do various things that require 2 inputs, like differential radiometry, which can also include what I call poor man's interferometry. There's correlation support, so there's a 2-input correlator. It's got a high-pass filter to remove DC offsets, and the high-pass filter is calculated based on the baseline and declination that you provide. And there's now a legend inserted into the radiometer data every few minutes. There's a one-liner that basically says what the data items are, which I don't know why I've never done that before, but it seemed like a really good idea to, if you have one of these data files and you're not sure what the fields are, there's a legend that gets emitted every couple of minutes in the data. So in the radio, we're going to talk about the data formats first, and then talk about the interferometry support. So for the radiometry side, as distinct from the FFT or spectral side, there's a bunch of data items that are produced in a data record. So many of you may remember the BAA data logger block that we put together for logging radiometry data. It's been enhanced to take a bunch of new inputs, and it, as I said, it emits a legend record. So the sum output is the sum of the A and B input channels. Now, if you only have a single receiver, there's you can basically have it take zeros from the second input, and there's a device syntax that allows you to do that. So obviously the sum would be exactly the same as just the A input all by itself. There's a correlator outputs for both the real and imaginary components. It's a complex correlator. Obviously, we're dealing with complex data from the receivers, so it's very easy to produce a complex correlator output. There's a difference output, so that's A minus B. There's just the total power for the east and the west, or A and B, depending on how you want to, what you want to call them. And then it indicates the current declination, the current frequency, and the current bandwidth. All the records are comma-separated values, or CSV.
Marcus, we are looking at your title slide. Is that what you want?
No, you should be looking at the second slide.
We're not in slideshow either. So we're looking at all of them on the left. I see 6 little blue boxes.
Well, that's just weird, because that's not what's on my screen.
Yeah, it's definitely the same here.
You need to unshare and then share the correct screen, I think, or window.
Yes, yeah.
Oh, yeah, I think I know what's going on. Okay.
That's looking much better. We're on slide 3.
Okay, we'll just, yeah, it's because of the way
show us slide 2.
Yes, sorry about that. It's just the way the sharing works.
It's not in display mode yet. It's still in, editing mode.
Yeah, what I did was I shared the specific application, but the problem is when you go into slideshow, it actually creates a new window, and that window would not be shared. So what I'm going to do is stop sharing for a sec and just share the entire screen instead.
Yeah, that works much better.
Okay, there we go. So I'll share my whole desktop. So how's that looking now?
That's the same as before.
Yeah, and then
I see slide 3 highlighted on the left.
okay, and now I'll do that. And do you see the full screen now?
Yep, that's the
Okay.
one.
All
Now
right,
we see
okay.
slide 3 big. We never saw slide 2.
Okay, so I'll go back to slide 2, where we talk about the new functionality. So 2 inputs, differential support, like I said, poor man's interferometry, which I'll talk about a little bit later, the correlation support, which includes a high-pass filter, and the insertion of the legend in the radiometer data. So now we'll move to slide 3. Where were we? So the BAA data logger block is what we had worked on the last time to log just a single channel of radiometer data, basically. And now, of course, we are emitting much more data in that our radiometer output. There's the sum, which is the sum of the A and B, or east and west. I use the two terms interchangeably. The sum of those two channels. The correlator output, which is the complex correlation of the east and west, or A and B inputs. And of course, because it's a complex correlator, it produces both real and imaginary outputs, or I and Q outputs, or cosine and sine outputs. The nomenclature is used differently in different contexts, but it's all the same thing. The differential output, which is A minus B, and we'll talk about that in a bit. And then, of course, just the individual east and west, or A and B power outputs. The current declination, the current frequency, and the current bandwidth. All the records are comma-separated values, which is used in a bunch of different applications out there. For example, Excel can read CSV files, and Octave and the Open Office spreadsheet app and all of that. They can all read CSVs, which is why I've been using CSVs now for quite some time. I used to use a more like a space-separated format, but a lot of my users said, hey, Excel uses comma-separated values, so I moved to that a couple of years back. All the records are prefixed with the current hour, minute, and second in both UTC and LMST. So you do have to provide your local longitude to the application so it can compute the local mean sidereal time. And the output format for the spectrometry side, it's the output of the FFTs for both the A and B, or east and west channels. And it's the PSD in dB full scale. So none of this is calibrated. SDRs, as many of you know, are typically not calibrated devices. So the signals that come out of them are just proportional to the antenna input voltage, and without being able to calibrate it using a calibration source and making some adjustments, you don't know what they actually mean in terms of the input levels at the antenna input. And again, they're comma-separated values. So again, the hour, minute, and second in UTC and LMST, and then just a whole bunch of comma-separated dB values. 2048, I think, is the default that we're using in the application. So that's the resolution of the FFT. So the differential support, it can be used for doing things like sky minus reference. So let's say you have a temperature stabilized terminator. Maybe it's a cold terminator. You can, the B channel or the west channel could be a reference. So you'd be calculating the difference between the sky and the reference. It can also be used to work as what's called a differential interferometer. And there's a document that I've referenced there that talks about this. Ken Tapping and I did that almost a decade ago now, I think, we did an experiment by using RTL SDRs, 2 of them, and using a differential mode. We were able to produce what amounts to 2 adding interferometers, but they are 180 degrees out of phase with each other. So rather than a fringe riding on top of total power data, which is what you get with a conventional adding interferometer, you end up with something that's closer to what you'd expect from a phase switched or a correlation interferometer. And you can also use this for beam subtraction. Ken has used that with only partial success for trying to subtract out the tropospheric response from the radiometer he was using for measuring the moon. The problem is at 12 gigahertz, the troposphere, clouds, rain, and all of that stuff actually does affect the amount of power received by the antenna. So he was using a pair of LNBs fairly close to one another. So one would be on the object, and the other would just be sampling cold sky plus troposphere, and then subtracting that out. Sometimes it worked okay, but the problem is the troposphere isn't reliably uniform across the sort of field of view of the two LNBFs. So you can actually use it for estimating weather by measuring the troposphere this way. In fact, it often at 12 gigs, it often seems to do better at being a weather predictor than it is at being a radio astronomy radiometer. Strict Dickey switching in SDRs and GNU Radio is awkward. Not impossible, just really awkward. Because in order to do it strictly correctly, you need hardware support for it in the SDR, and there just isn't in most SDRs unless you modify FPGAs and use GPIO inputs and that sort of thing. And GNU Radio also, it operates on streams of samples, and the buffering is often quite large. So when you state switch, you don't have a really precise notion of which samples correspond to which switch state. Now, if you switch relatively slowly, like once every second, then you can just sort of throw away samples after a state switch. And that does work after a fashion, but you do sometimes get contamination and you get out of sync a little bit. So that's why I started playing with this differential stuff a few years back, because you don't need any synchronization with any switching machinery. Now the correlation support, so a correlation interferometer, so it's a 2-input correlator between the A and B channels or east and west channels. It calculates the conjugate multiply, so it conjugates 1/2 and then multiplies it. That is a pretty standard way of doing this, particularly when you're low-pass filtering the output, because that tends to maximize the correlation response when you conjugate one of the signals. The output, of course, is what we call a complex interferogram, so it's the interference fringes you're all used to, but it has 2 components that are 90 degrees out of phase. Obviously, doing this properly requires a coherent 2-channel radio, like the USRP B210 or the Lime SDR, the 2-channel one, the Lime SDR USB, or the Blade RF 2.0. They all will support coherent inputs. Back in the day, correlation interferometer, actually any kind of interferometer, particularly as phase switching, for example, was a modestly challenging hardware project. Now with these types of SDRs, it's almost a no-brainer to be able to build a correlation interferometer with these types of radios. And a good correlator tends to reduce artifacts that plague regular radiometers. So a lot of times I see amateurs saying, oh, I've got a few $1,000s to spend, I'll go out and buy the biggest dish I can find that I can reasonably put in my backyard. And what I tend to recommend is sort of redistributing that budget to 2 smaller antennas and a better radio, a coherent radio, because interferometers, they just want to work. You can put one together, particularly a correlating interferometer, and start observing the usual pantheon of objects, you know, literally within days after you getting it set up. You don't have gain drift problems. You don't have any of the other problems that tend to plague a single dish radiometer. Okay, so we've covered basically the slide set, and what I'm going to do now is go into the application, into GRC. Oops, just switch to an empty flow graph. Let me just get rid of that. Okay, so we're now in the BAA seminar application. Pulled it into GRC, or GNU Radio Companion as it's called. And I'll go over some of the new stuff that has been added. I can't remember last time whether we had virtual syncs in this or not. We probably did. There's something that is a layout convenience. It means that you don't have to have a lot of these lines all over your graph. So if you have blocks that are, let's say you've got a source block here and you've got some downstream blocks in another corner of the graph, you don't have to extend lines all the way over to that corner of the page. You can use these virtual sinks and virtual sources. They're like just connectors, and it just keeps the graph looking a lot tidier. So you can see here, actually, you can see that we now have 2 outputs coming from this Osmocom source, and we've labeled them RF1 and RF2, not a very surprising name. And they are then used all over the place. So the various functionalities, like the spectral part is here. You can see there's 2 FFTs that start with a virtual source for each of them. We have to convert to a vector. We covered this last time when it was just a single RF channel. So something here that may not be obvious. We actually put in an add constant on the second channel. We add just a tiny little bit to the output, because the output could be zeros of that FFT on the second channel. If the second channel isn't real, if it's just the zero device on Linux, and I'll show you how to do that later if you only have a single radio. So that could be zeros, and of course when you try to take a log 10 of that, it'll blow up. So what we add is a tiny amount of a constant of like 10 to the minus 14, which is tiny, and it's not going to actually affect anything if you actually have a receiver in there. It's just to keep the log to the base 10 from blowing up. So then we have these 2 outputs, FFT1 out and FFT2 out, and we use them a bit later right here. You can see there's virtual sources here and here, and we have this BAA flipper block that we constructed last time, and it's used if you're displaying the spectrum in terms of Doppler or redshift. Because of the science conventions about redshift, you have to flip the spectrum around before you calculate the Doppler and display it and log it and all of that stuff. So that's what that block is there for. And it's got a control that either says the flipper is enabled or not, depending on whether you're actually interested in Doppler data or not. Sometimes the spectral part, if you're not observing, let's say, at the OH line or the hydrogen line, the spectral part of this is mostly used for looking for RFI. So you don't actually need the Doppler stuff. You just want the actual frequency. So in that case, the flipper would be disabled, and you can control that from the command line. So we'll go back here, and feel free to ask questions at any time. So again, we have the two RF sources. We convert to the complex to mag squared, which basically gives you the instantaneous power estimate. It's like a diode, only better. And then we have a two-stage integrator here, which we talked about last time. And then there's a bit of complexity here, but so you can see here that we're computing the sum and the differences, as well as the actual raw channels. So we need these other virtual sinks. The other thing we do here on the subtract path is that because we possibly are using that for poor man's interferometry, we actually have what amounts to a DC block or high pass filter in the path here, just in case you're using it for that, and that allows you to just have a high pass response. And what that does is it will effectively eliminate things like DC offsets in the interference pattern, or the fringes, typically caused either by DC offsets in the hardware or a constant RFI source somewhere in your input pass band. So we just high pass filter that before doing the final subtract. So then we have another couple of virtual sinks here, the sum out and the difference out. And back here, of course, there's just the raw total powers for the two sides. And this is our correlation path. Now this shouldn't be here. I'm just going to delete that. That's a leftover. They're disabled, but they're cluttering the graph, so I'm just going to disable them. So the correlator here takes the two RF inputs here. You can see RF1 and RF2. It goes into that multiply conjugate block that I talked about earlier. So multiply conjugate is basically it conjugates one side and just multiplies it, does a complex multiply. Again, there's a two-stage integrator here, but there's this lower path, which is a much longer time constant integrator, and we subtract the two. So that's a very cheap way of implementing a high-pass filter. Now, if we look at the parameters on this block, you can see that there's this thing called FPER used to calculate the corner frequency, or the alpha value for this single pole IIR filter. FPER is the fringe period. So when you're using this and you actually really care about the interferometry outputs, there's this variable here called FPER, which is the fringe period. And we just call a function in our RA-funcs module that we talked about last time for calculating fringe periods, given the center frequency and the baseline length in meters and the declination. And that calculates the fringe period. And then we use that to calculate the parameters of a high-pass filter. And it's actually reasonably effective once it converges, and we'll see that when we're running it in a minute. If there's any DC offset tendency, either due to RFI or just small DC offsets in the receiver, once the high-pass filter converges, the signal just sits right around zero, very close to zero, unless you have an actual object in the beam. Now, unfortunately, it's far too cold outside for the last several days for me to have actually set up interferometer antennas outside. There's just no way I can work in that kind of cold on fiddly things like antennas and amplifiers. So I have a radio in here. I have a B210, which is a dual coherent channel thing, but it's not connected to any antennas. So you're just going to have to imagine fringes coming out of it from the sun, which was the plan. The plan was to set them up pointing along the path of the sun so that we'd see nice fringes coming out, but it was just too cold for me to set that up. So once we've done this subtract here, which is the last stage in this high-pass filter, we have an integrator, just like in the total power paths and so on. And we can multiply the detector output if we want. Or in this case, it's a correlator output, but there's a parameter called detector multiplier, which is it's like the DC gain on a conventional old style analog radio telescope, just to make the output values perhaps a little bit more obvious in the displays and in your logging. Although even single precision floating point, which is what we use here, has tons and tons of dynamic range. So it's very, very rare that the signals will drop off the bottom of the dynamic range of these single precision floating points. Now, if we go back up here where we do the logging, so the BAA logger, I went back and forth on whether it should have multiple inputs, like one input per data value, your total power east and west, and your sums and your differences and your correlator outputs. But that would be messy and error prone and perhaps harder for people to understand. So instead, what I do is all of the different data values go through this thing called a patterned interleaver before they go to the logger. And the logger knows how many channels it's supposed to be processing from the input. So if it gets a lump of data, a vector of values, it knows that those are interleaved values, and it pulls them off in order and logs them as separate values in the log files. That was easier. Well, not easier, but I think it was more straightforward, and means that if you want to add data values to the logger, you don't have to change the logging function at all. You simply tell it how many channels are interleaved in the input. And with the legend that we put in, it makes it very straightforward to add new values that are logged with that data logger. Yeah, so if we look at the data files that it produced yesterday, actually, when I was running the application, we'll bring one of these into an editor just to show you what they look like. Now, I only had it on for a couple of minutes, not even long enough for the legend to get output. But you can see what they look like here. There's the UT time and the LMST, and then the data values. And all just comma separated and floating point values. We'll look at the corresponding FFT one. So the FFTs aren't logged nearly as frequently because they're much more voluminous, and you typically don't need very frequent logging of FFT data. And you can see it goes on and on and on. I'm not going to count it here for you, but there's 2,048 values on each line. And you can see they have values like minus 87.98, and that's a, that's a dB value relative to full scale. Are there any questions so far?
Yes, Marcus. There's your editor didn't show any roll labels, and earlier you said you had added roll labels.
Actually, it's column labels, and yeah, there's this thing here. There's this thing here called legend. But the thing is, it only puts that out once in a while, and it's been a while since I looked at that code, but I think what it does, why don't we open that code in the editor?
It would be very handy to know what sort of declination you're on when you look back in the data, you know.
Yeah, and that's the idea behind putting out the legend, but the legend only gets output once in a while. So let me take a look at this.
It should be output at the beginning of a file, like a file header. It really don't need to be output every 30 lines.
Well, the thing is, because other parameters can change at runtime, it outputs it. I'm just trying to see where it actually does that. It's been a while since I looked at this code, as I said.
And what makes it a header? Is there a magic character as the first character or something?
Actually, no. Oh, yeah. You can see here what it does is it puts out a tag info : before it puts out the rest of the legend. So that's easy to filter. But you're right. It should put it out the first time it writes a record to a new file. And that's a mod that I can put in. I won't put it in here. So right now it's just basically putting it out every 30 records. But I mean that could change. Having it put it out whenever the log parameters change, like the declination and frequency and bandwidth, that could be done as well. So rather than just putting it out on a regular basis, it just puts it out when that stuff changes.
That would be good.
Yeah, I'll take input from that. You have my email address, so.
Sure, thanks. I have one more question.
Sure. Yep, go ahead.
How does the integrator work? Could you explain a little more how the integrator block works?
Okay, so the integrator block in GNU Radio simply sums. It just sums the input values. So right here you see an integrate block. Right here. And it says decimation 100. So what that means is it takes 100 input values and sums them, and then outputs a single value once that sum is done. So it's also a decimator. What I did, and if you're here for the previous seminar, I split the integration between the integrate block and a single pole IIR filter. And I did that just so I could achieve the desired sample rates. The single pole IAR filter doesn't decimate. It's just a filter, whereas the integrator does integrate and decimate. And the reason I split them in the first place was that, remember I talked about single precision floating point values. They most of the time have enough dynamic range, but in the particular case of the single pole IAR filter, if you have very small alpha values and relatively high data rates, you run into some fairly severe numerical errors just due to the precision. And GNU Radio doesn't do double precision signal processing. So instead of doing it all in a single pole IAR filter, I split it between an integrator block, which handles part of the problem, and then the single pole IAR filter does the rest. Does that answer your question?
I gotta dig into it a little more, but yeah, that's good. Thank you.
You're welcome. Any more questions? Okay, so what I'm going to do is actually run this thing. Yeah, maybe I'll just minimize that instead. So you can see it looks a little bit different than last time, just because we've added the correlation display, and the total power display now includes all of the sort of radiometry stuff. So the sum and difference for the detector for the two channels, and then just the separate detector channels for east and west, or A and B. Same thing. So if we look down here. Now, keep in mind, we don't have this hooked up to an antenna at all. You can see the various bits and pieces are starting to get logged in the total power display there. And the USRP doesn't necessarily have perfect gain balance between the two channels. Even when there's no antenna connected, they may not have precisely the same power output value, which is what you can see here. The total power east is quite small. Yeah, you can see it's tiny, and then total power west is quite a bit larger. Part of that is because I have two different power inserters on the thing, and one is probably noisier than the other. And if you look at the correlation output, it will be heading for 0 on the real and the imaginary cosine sine, but the high pass filter still has to converge. But the values, as you can see, are quite small. And over the next, minute or so, they'll both converge down to 0. There's a controls panel. I can't remember whether we had that there last time or not, but it allows you to change some parameters at runtime, like the spectral integration time and the total power integration time, the detector output multiplier, tune frequency, RF gain, and the current declination and baseline length. You can see here it also displays the fringe period that it's calculated based on the frequency, declination, and baseline length. So that's about 20 minutes, and with a paltry 4-meter baseline, that's about correct at 21 centimeters.
Baseline length is what, meters?
Yes. I was going to put it in furlongs, but I think that would confuse people. There's the spectral output. This is just because it has no input, so it's mostly seeing the DC offset, residual DC offset spur in the radio. But that generally goes away when you have an actual input, because the input will completely swamp that.
Marcus, talk a little bit about the gain requirements for in this case, the east and west channels here from a hardware standpoint.
Oh, like the analog gain?
Yeah, from a standpoint of how close that has to be matched, and
Okay, yeah. Yeah, it's generally a good idea to gain match, within a dB or so, the two halves of the correlator. And you can usually achieve that in practice, with relatively ordinary commercial LNAs and so on. You can use attenuators in line to basically bring the louder channel down. What I found is that they're typically within a few dB of each other in any actual installation. It's just an attribute of RF hardware tends not to, if you get two random samples of the same piece of hardware, their gain characteristics are often different by a dB or so. And of course, once you have a few of these objects in your signal processing chain, you can get fairly significant gain differences between two chains.
Can we save money and somehow do that in software?
Yes, absolutely. Although, I mean, you have to be careful. You need to make sure that sufficient bits are being lit up in the ADC on both sides. So you don't want there to be a very large gain difference between the two sides. But minor gain differences, absolutely. You could simply add multiplier blocks to the two halves to change the gain. I've done that in the past. I just haven't put it in this particular application yet. But if people are interested, I could put in gain compensation on the two sides. In fact, you can do it. You can automate that. I did that in the past in one of my interferometer apps. So in the first minute or so of operation, it estimates the power in the two channels and then calculates a compensation in the multiplier that it needs to use to make them even. You don't need
to balance that somehow by putting a gain on both, or is just a gain on one side?
You could do it either way. I mean, you could basically split it between the two sides and decide that half of it is a positive gain on one side and a negative gain on the other.
But there has to be two blocks so that the timing works out?
Yeah. The other thing that you can do, which I haven't discussed, is so in any actual interferometer, there will be very minor cable length differences or phase differences between the two halves of the interferometer. And you can trivially compensate for those as well, just using a complex multiply in the input. You simply, if you know how many degrees of phase difference there is between the two sides, you can it's a straightforward calculation to just put that into a complex multiply and phase rotate one side so that it's ahead or behind. You compensated for the ahead or behind of the other side. And again, I've done that in the past. In fact, I think current spectroradiometer, which has interferometry support, you can turn on automatic fringe rotation, so or fringe stopping. So what that does is it tracks the fringe period as the object moves across your interferometer, across the phase center of the interferometer, and actually stops fringes from actually being produced. So the idea is to keep the response of the interferometer maximized, and you can use that for doing things like pulsar monitoring, where you need a constant output from the correlator in order to do your pulsar stuff, and you can just fringe stop if you have a good model of the fringe rate. It's actually fairly straightforward.
You speak of knowing the timing between my two different coaxes. We can put in a delay and then like rotate a knob till it looks good, or what?
Yes, absolutely. Yep. Delay and phase rotation. I mean, hopefully, hopefully your cables are matched well enough that you just need a phase rotation rather than a single sample delay or multiple of single sample delay. Because obviously you'd need two different blocks to do that. There is a delay block in GNU Radio, and phase rotation is just done with a complex multiply. So yeah, I've done that in the past where you have a control, a slider that you move around until you've got your phase center where you want it. And again, that could be added to this relatively easily. It's just you'd have to put in more blocks in the high-speed part of the path, so that consumes more CPU cycles, because that has to be done at the input sample rate. It can't be done after correlation and low-pass filtering. So, I mean, you're effectively doing the digital equivalent of stretching or compressing your coax line, and that needs to be done at the input sample rate.
I'm trying to think this out. As I tune the knob, what am I looking for? What's a good result? You say a zero phase.
Yeah, that's actually an interesting question. I think what I would do is I'd use a fixed calibrator source. So what I would do is I would put a signal, a noise source in the far field, right at the phase center of the interferometer. I mean, you may not actually have room to do this, but if I were doing it, that's what I would do. And then I would adjust the correlator output for the maximum correlation. And it may actually be somewhat awkward to make that work, depending on how much space you have in your backyard. Because ideally you want like a calibration source in the far field of the interferometer. And oriented so that it's, perfectly perpendicular to your baseline and all of that stuff. But you can also use a calibrator source, like you wait for, Cygnus A to go through the radio telescope, and you play. Now, granted, with a transit instrument, this will have to take place over several days, where you play with the phase offset until the maximum of the correlation occurs exactly as Cygnus A is transiting your meridian. at large observatories, they do this all the time. They use a calibrator source, but their antennas typically track. So they just track Cygnus A and then, adjust their phase estimates until they're getting the maximum correlation output. I mean, in practice, if you get it close, analog-wise, you'll probably be okay. If you look at what Jim Abshire did several years ago, he had a 400 megahertz interferometer in his backyard. It was a phase-switched interferometer. There was not a whole lot of phase length compensation in the signal processing chain, and he was able to produce quite decent images, aperture synthesis images from Cygnus A. So my suspicion is that if you cut your feed lines from the same spool of cable and you're reasonably careful about the way you do it, you'll probably be okay. And the digital phase compensation is a flourish that you might add later to get better fringes. But in this case, better fringes just means that the fringe maximum occurs precisely at transit.
So how much can I cheat here? If my coax is wildly different lengths with a delay or a phase shifting, how much can I cheat?
Well, with the delay in the phase shift, you can compensate for arbitrary lengths. The performance difference, there's no performance difference whether you have a delay of 100 samples or a delay of 5 samples. Once those blocks are in the flow, they're consuming cycles, and the delay, except for memory occupancy, the delay, there's no performance difference based on the delay. But
And
yeah,
so
I mean,
I could trade software for hardware there again.
absolutely you could. Yeah, absolutely you could. When I built interferometers in the past, I've always made certain that the cable lengths were very close to identical. But yes, absolutely possible.
In fact, with actually kind of random arrays, isn't that what is involved in those to begin with? I mean, they're all.
Yes, absolutely. Yes, right. They had delay compensation, both. Well, they do delay compensation for a number of different reasons. One of which is that when you have an interferometer that has a very large fractional bandwidth, you actually need to insert delays in order to keep the correlation close to maximum, because as the object, moves, so there's a lot of parallax between the baseline. The baseline orientation and the object itself. With very large bandwidths, you get geometric delay, geometric decorrelation, and the way they cure that is they insert delays into the processing chain to keep that from happening. With amateur interferometers, you tend not to run into that because your fractional bandwidths are going to be quite small, and your baselines are going to be, much more modest. So, for example, when CCERA builds an interferometer, maybe next summer, it'll be at 21 centimeters and a maximum of about 20 megahertz bandwidth. And so that fractional bandwidth is tiny, and our maximum baseline is likely to be much less than 100 meters. So we don't have to worry about that. We just have to worry about cable lengths. And of course, the effective cable length, the delay on the cable will change with ambient temperature. So if you have any differential heating or cooling of the cables, then the effective cable length will change. And that's actually a very interesting topic all to itself. DRAO, for example, they have a 7-element Earth rotation interferometer, and they actually have active analog cable length compensation. So they basically, I read the paper years ago, but it's actually quite ornate, and they send a signal down the cables, and it gets rotated back at a different frequency, and then they do phase measurement of the calibration signal, and they insert analog delays into the cables to compensate, and they do that in real time. So they're constantly evaluating the effective cable length of the cables during the day. But their cable lengths are quite long. I think the maximum span of that interferometer is just over 1 kilometer. So you know, the effective cable length can actually change considerably over that length of cable. But as I said, my experience with the interferometers that I built is that I haven't actually needed dynamic cable length compensation. I put it in my application just because it's a nice to have, but I hardly ever use it. Once I start looking into aperture synthesis imaging, I may care more about that. Any other questions? So yeah, if people have suggestions or more comments, you can email me directly. I think Paul has my email address and can publish it to the BAA list. Yeah, I'm happy to take questions.
Marcos, from the standpoint of what this all should look like when it's being properly used, I know there are textbooks about what interferometers, the fringe patterns look like and all that sort of thing. Do you have any past examples of what
Let me
this
just,
looks like?
yeah, let me just see. Not in this particular application, but in sort of reduced data, I might. There might be something on the CCERA site that I saved.
And also, kind of as a follow-up question to that, I seem to remember a few years ago, and maybe I'm just making this up, but that there was a software application or something, maybe even involved hardware, that was a simulator for being able to simulate different interferometer conditions. And I don't know where I ran across that, but
Yeah, I vaguely recall it too. It wasn't mine, so yeah, I'm not sure. Unfortunately, it doesn't. Oh, well, maybe this might be a. Yeah, there you go. There's. Can you see that?
Yep.
Yep. So that was that's Virgo A from our 600 megahertz interferometer that we ran a couple of years back. So it's got the cosine channel and the sine channel and the and the square root.
Okay.
So yeah, it's the square root of the square of the cos and sine components actually gives you what's called the complex envelope. So the response is very similar to what you'd expect from basically the convolution of the response pattern of the two antennas. So very similar to what you get with a single antenna radiometer, except that it's actually derived from the interference fringes.
Right.
And this one's actually relatively well balanced. As you can see, it's almost all of the DC offset is removed. Virgo A is not that strong a source compared to, for example, Cygnus A or Cassiopeia A, but I don't think I have that data lying around, unfortunately. I just happened to see it here near the end. I had to do a cleanup of a lot of the files on this website, and some of the interferograms are gone. I apologize. But hey, at least there is a Virgo A1.
Yeah, well, I mean, it gives us an idea of what it would look like.
Yep. It's actually really neat when you first get your interferometer going and you see the fringes appearing in the display, and they're generally relatively clean, particularly for the stronger sources. And again, because interferometers tend to reject any signal that doesn't strongly correlate on the two sides. So random noise from the two sides doesn't correlate, and it tends to integrate out to zero. So the fringes tend to be relatively pretty.
I think that's an example of a point source.
Yes.
There are other point sources like that. What actually happens when you go through a galaxy plane or something? What
Well,
shows up?
An interferometer will tend to reject sources that are larger than the effective resolution of the interferometer. So you'll basically get zero. So it tends to subtract out the galactic background. So extended sources, either you reduce the baseline so that your effective resolution is much fatter, or you use the radiometer outputs. Again, this application logs not just the correlation output, but the outputs of the individual antennas. So you can do some post-processing to sort of add in the backgrounds. Let's say you're building an image of the sky from interferometer data and the larger scale data. You'd use the radiometer outputs, but they're not very nice typically in an amateur project. So many people will, they'll go out and they'll buy a 15-foot dish and put a radiometer on it, and then discover that radiometers at the amateur scale tend to be, they tend not to achieve their theoretical sensitivity by a very large factor. So if the theoretical sensitivity for, let's say, 1 minute integration is, I don't know, 5 Jansky, the actual achieved sensitivity is more likely to be 50 Jansky. So they don't do nearly as well as an interferometer.
I'm trying to figure out what this would be like if I actually had 2 tracking dishes. And I guess it would just stay as a large green signal on your last picture.
Yeah, so it would actually, no, the fringes result from the transit of the object across your baseline, regardless of where your antennas are pointing. So you still get fringes when you're tracking. That's the thing that most people kind of miss. If you're tracking the object, you still get fringes, because you're effectively sampling this virtual grating that appears across the sky that results from the baseline of the interferometer itself. And it doesn't matter whether the antennas track or not. Let's say the beam width of your 2 antennas is 5 degrees, then you only get, if you're not tracking, then you only get about a minute's worth, minute and a half's worth of 20 minutes worth of fringes, 25 minutes worth of fringes before the object has moved out of your beam. But if you track, your fringes will you'll be able to get fringes for a much longer time while you're tracking the object.
But if my dishes were on a football-sized turntable, they wouldn't, because the whole turntable would rotate, and therefore the time difference between those, there'd be no phase delay for one dish compared to the other.
Let me think about that. I'm trying to think of whether that's equivalent.
We're getting fringes because it's a slightly different distance to the star than before.
Correct. Yes.
or between the two of them.
Yes. Correct.
The
But your
difference
baseline,
between the two is changing in time.
correct. And but keep in mind that due to Earth's rotation, that baseline is not staying perfectly perpendicular to the source. It's rotating as well.
That's right. And so that's why my football-sized turntable to hold the two dishes. We're talking
Right.
a remarkable project.
Right. Right. But yeah, there's plenty of treatises out there about interferometry put out by NRAO and universities all over the place, and they're all over the web. Some of them are more accessible than others. Some of them are very math heavy, and some of them are much more introductory. And I'd recommend looking at those. And some like the NRAO one is actually reasonably good because it starts out kind of light and doesn't get super heavy until near the end. So you can have some epiphanies about how all this works and the things you can do without getting too math heavy. For example, the aperture synthesis imaging turns out to be a lot easier than I ever suspected it to be, which is why we're going to probably pursue that next summer with an east-west interferometer with variable baseline using Earth rotation synthesis to produce images. And it, I mean, all you basically do is you take the fringes that you've recorded at various baselines and run them through some matrix math, some coordinate rotations, and so on, and you end up with an image. So I mean, that's something.
And what would you aim at? My understanding is something around the north celestial pole would be the easiest spot because then you have, I guess, more geometry working for you.
Actually, Jim, for example, just aimed at or at Cygnus A, which at his location is almost overhead, as it is for me, and got several hours of fringes for every pass. You need to get enough fringes that your baseline is rotated enough to give you, some amount of spatial resolution.
Marcus, this question may have already been resolved, and I just don't remember the answer, but is it with the standard TV offset dishes that are the small ones, 18-inch ones or whatever that are available, is it worth trying to do anything with those relative to interferometry? Either I went blank or somebody did.
Marcus, are you still with us? Or has your line broken?
Okay, I'm back now.
Oh, okay. The question I just asked, Marcus, was, is it worth trying to do anything with, and this question may have been answered several times before, but I just don't remember the answer. Is it worth trying to do interferometry with the standard small satellite TV dish, offset dish, the metal ones that you see all over the place? Is that a worthwhile effort?
Well, it depends on what frequency you're targeting.
Yeah.
If you're going to be using the existing LNBs, you actually can't because they down convert the signal into L-band, and because the oscillators that are used to do that down conversion are not mutually coherent,
Right.
it won't work. In terms of the dish itself, it may be just large enough for 21 centimeters.
Uh-huh.
And yeah, if you made a 21 centimeter feed for those dishes, that you could probably do some bright source interferometry with those, like Cygnus A, Cassiopeia A, maybe Virgo A, and a
Right.
few others.
Okay.
I have one of those dishes in my backyard with just a wire dipole made out of copper, and
Yeah.
I could pick up the galaxy anyway.
Right. So the hydrogen line and that kind of thing.
Right.
Yeah.
That's all. It's pretty
Yeah.
weak. I need to improve the antenna.
Yeah. Yeah, those dishes are kind of hard to illuminate. You need a high gain feed on those because they're effectively a very long focal length. So a simple dipole feed probably doesn't have enough gain to properly illuminate the dish, because the feed tends to be further away than a prime focus dish.
Mm-hmm.
What I would do for one of those dishes, and I've done this in the past, is use a full wave loop feed with a backing plate. They tend to have about 5 to 6 dB more gain. Maybe not 5 to 6 dB, maybe 3 more gain than a simple dipole, and they'll actually illuminate the dish a fair amount better than a simple dipole feed.
Mm-hmm.
Thank you for your comments. This is a progression of experiments. Yes.
Yeah, absolutely. Absolutely. Yeah. What I was going to set up for today, but it was too cold, is I have a pair of these paragrid antennas. They're sort of an elliptical parabola made into a grid. They're cast aluminum, and you can buy them on the internet for point-to-point Wi-Fi and that kind of thing. And Newelec is selling them for the GOES satellites as well. They have a 21 centimeter feed assembly that that's kind of in beta test at the moment. I have one here. Those antennas, they're about 1 meter in one direction and about 2/3 of a meter in the other. And they have a dipole plus reflector feed that's optimized for that type of dish, and they work really well. And so that might also be something to consider for a relatively inexpensive interferometer that you don't even necessarily need to have tracking, because the beam width is so large that you know, if you point it sort of vaguely in the direction of where you expect Cygnus A to transit, for example, you'll probably get several hours of fringes out of it, which is great because you can then use that for Earth rotation synthesis. But before you do that, just getting fringes at all is the first step, because that kind of teaches you how your interferometer works and the things to consider and whether your electronics are any good and all that kind of stuff. So, and then once you're reliably recording fringes, then you decide on several different baseline lengths. You mark them fairly precisely so that you know exactly what the baseline length is for each of your fringe sets. And from there, you can then do aperture synthesis.
Okay.
Marcus, thank you very much for your time, both this afternoon and in the time invested in preparing the exercise. Fantastic. Thank you so much.
Oh, you are most welcome, as always.
If there are any questions, do pass them on to me or to Marcus direct if you have his address. Otherwise, I'll forward them for you. And otherwise, I think that's it for today. Again,
Okay.
Thank you. There'd be a resounding applause for you if we were in real space. But we'll see you again sometime, I'm sure.
Yes, absolutely.
And for the video.
Yeah, I'll send out the link for the video in due course. I'll render it now.
Yeah, and you'll probably have to do a lot of editing for all the missteps and stuff, but
no, we're good. I paused it while you were getting your comms sorted.
Okay. All right.
Cheers, Marcus. Well done.
Yep.
Thanks very much.
Thanks very much, Marcus.
You're
now.
all are most welcome. See you all later.